Hello dear learners, welcome to the online course on electricity and electrical wiring. This is the second lecture of module 7 on electrical house wiring. In our first lecture, we learned that electricity is generated in power plants. The generated electricity is then transported through a network of transmission and distribution lines to locations near the consumers. From there, the power is supplied to consumers through the service mains. We discussed about the different types of distributors and service mains used by authorities to deliver the power to consumers. Lastly, we explored some of the key electrical accessories used in house wiring. Okay, now for determining the number of switchboards, there are no specific calculations involved. It mainly depends on location of the loads and the customer's requirement. The number of control switches required will be equal to the number of load points. Normally for light and fan loads, 5 ampere and 6 ampere switches are used. For power loads, 15 ampere or 16 ampere switches are commonly used. Fan speed regulators may be used for controlling the speed of ceiling fans. So for convenience, the switchboards controlling the lights should be installed near the entrance to the room. Power appliances, the switchboards can be installed close to the appliance using accessories like 15 ampere or 16 ampere combined switch socket units. Appropriate IS codes must be followed for location and rules in this case. Now, to decide the size of the distribution board, we first need to determine the number of sub-circuits. In this case, the distribution boards needs to accommodate 5 single pole MCBs for the 5 sub-circuits. Next, an additional MCB may be provided as a spare for future expansion. For additional safety and convenience, the incoming supply to the distribution board may also be connected to a double pole MCB or a double pole isolator. This would also act as the main switch for the DB. Therefore, the size of the DB required in our case will be A2A distribution board. So this is a picture of a A2A distribution board. So now that we have determined the number of sub-circuits, switchboard and the size of distribution board, let's move on to determine the size of wires and breakers. The size of wires should be selected based on 3 key parameters. Number 1, the current carrying capacity or current rating of the cable. Number 2, the voltage drop in the cable. And number 3, the minimum permissible size. According to IS code 732, the minimum size of cables to be used for lighting circuits is 1.5 square mm for copper cables. For power circuits, the minimum size is 2.5 square mm. So before we look at the steps to determine the cable size and breaker ratings, let's first understand the important parameters needed for the calculation. The first parameter is the current rating of the cable. The current rating of a cable is the maximum current it can safely pass under any given ambient condition. Normal standard tables are available where the current ratings are specified at a specified reference condition for different sizes of cables. However, if the cable is installed in an environment that differs from the reference condition, a correction factor must be applied to the cable's current rating. The actual current rating is therefore calculated by multiplying the reference current rating of the cable by the appropriate correction factors. So these correction factors depends on various factors such as what is the ambient temperature, what is the condition of the installation site, how many number of cables will be bundled together, and all this. So you can refer to IS code 732 for more details on correction factors. Although cable sizes are specified in different ways, the most common methods are cross-sectional area of the conductor in square mm and the second one is standard wire gauge, that is SWG. So in the table you can see the current ratings of different sizes of single phase copper cables in square mm. The first column, it refers to the size of the cables in square mm. The second column, it refers to the rated current at standard conditions. And the third column, it refers to the approximate length of cable at which there will be a voltage drop of 1 volts when the rated current flows through the cable. Okay, now let's talk about the design current of a circuit. The design current is the current for which the circuit should be designed. It is obtained by multiplying the actual current by a safety factor. The actual current is the current that is expected to flow through the circuit under normal conditions. So this can be calculated using the total load in the circuit, which is represented by P in this equation, and the supply voltage and power factor. If the power factor is not known, it is typically assumed to be 0.9 for lighting circuits and 0.85 for power circuits. The safety factor, on the other hand, is usually taken between 1.2 and 1.5. So whenever current flows through a conductor, there will be a voltage drop due to the resistance of the conductor. As per IS code 732, the maximum permissible voltage drop in cables is specified. It is 3% for the lighting circuits and 5% for power circuits. So now to calculate the voltage drop, we use this particular formula. This formula requires a few key values. First, the length of the cable for which the voltage drop is to be calculated. Next, we need the cable's length in meters that causes a voltage drop of 1 volt at its rated current. This value is typically provided in the cable's specification sheet. In this case, it is provided in this third column. Finally, we need the rated current of the cable and the design current of the circuit in this equation to find out the voltage drop. Now, let's go through the steps to determine the cable size and breaker size for a circuit. Step number 1. Calculate the actual current of the circuit as per the connected load, then determine the desired current by applying a suitable safety factor. Step number 2. Select the breaker. Now the breaker rating should be chosen such that it is greater than the design current. Typically for lighting circuits, we usually use 6 amperes or 10 ampere breakers. These ratings conform to the 800 watt limit. For power circuits, we normally use 16 ampere or 20 ampere breakers. These again conforms to the 3000 watt limit. Step number 3, select the cable size such that the cable rating is greater than the breaker rating. However, while selecting the cable size, the actual cable rating must account for installation conditions by applying the appropriate correction factors. So, designed current should be calculated first. Based on design current, we will calculate the breaker rating, and then based on the breaker rating, we will determine the size of the cables. After that, step number 4, we have to check the voltage drop. Now calculate the voltage drop for the selected cable size and the cable length. If the voltage drop is within permissible limit, then we can use that particular cable. If not, we have to repeat the entire process using a higher rated cable. We can follow these steps discussed earlier to calculate cable sizes for sub-circuits and for cables connecting the load to the switches. In these circuits, each cable is expected to carry the full load current when in use. However, it is unlikely that all the connected loads in a house will operate simultaneously. For example, it is very unlikely that the geyser and the AC will be on at the same time. Also, all the lights and fans will be on at the same time. This is very unlikely. All the socket outlets will be used at the same time. this is also very unlikely. So this means the maximum demand that we can have at any time will be less than the total connected load. This ratio of the maximum demand and connected load is given a term, that is the diversity factor. So if the main circuit is designed based on the probable maximum demand rather than the total connected load, significant cost savings can be achieved. Using the diversity factor allows us to select cables with smaller cross-sectional area. This results in both cost and space savings. Therefore, for the main circuit, this design current is calculated by multiplying the actual current with the diversity factor and the safety factor. Please note that the diversity factor is applied only to the main circuit and not to the sub-circuits or the point circuits. The cable size for the main circuit can now be determined using this adjusted value of design current. Now let's determine the cable size and breaker size for our example problem. If you look at this table, for the first light and fan sub-circuit, the total connected load is 505 watts. For this load, the design current calculated is 3.5 amperes. So for the lighting sub-circuits, the power factor we assume is normally 0.9, and for power loads, as we have discussed, the power factor is normally assumed to be 0.85. The safety factor here we have considered to be 1.5, and for the cable ratings we assume that the correction factor is equal to 1. Now, as we have discussed earlier, the breaker current rating should be greater than the design current. So some of the commonly available single phase breaker ratings are 6 amperes, 10 amperes, 16 amperes, 20 amperes, 25 amperes, 32 amperes, 40 amperes and 63 amperes. So with a design current of 3.5 amperes, breaker with a 6 ampere rating can be chosen. According to the trip characteristics, the breakers are also classified as B type, C type, D type, etc. Each of them has different trip characteristics. For resistive loads, B type MCB is more preferable. For load with resistance and inductance, the C type is preferable, and for highly inductive load, the D type of MCB is preferable. Okay, so after selecting the MCB, we can now determine the cable size. We have discussed that the cable rating should be higher than the breaker rating. Therefore, based on this relationship, a cable of 1.5 square mm with a current rating of 10 amperes is suitable. Note that here we have assumed that the voltage drop is within the permissible limit. However, for actual installations, the voltage drop must be checked using the approximate length of each cable and the process that we have discussed earlier. The rest of the cable sizes are also calculated in the similar manner. For the main circuit, the diversity factor we have considered it to be 0.9. So these are the available current ratings of various MCBs. Okay, so let's now talk about a different topic where we can connect or give supply to different floors of a building. This concept is the concept of rising mains. So what we do in rising mains is, if you look at this diagram, that there will be how many floors were there? That many number of distribution boards will be installed in each floor. Now, this main circuit breaker will feed the distribution board of the ground floor, and the distribution board of the ground floor will in turn feed the first floor, and so on. So this concept is called as the rising mains. However, there is a problem in this particular concept or in this particular arrangement. The problem is, if a fault occurs in the rising mains, then this main circuit breaker is going to trip and the entire building will black out. Therefore, we have this next arrangement where we have a additional distribution board, which is the main distribution board. So from the main circuit breaker, we will provide connection to the main distribution board, and from the main distribution board, every floor's distribution board will get a separate feeder. This way, if something happens in one of the feeders, only that particular floor is going to get affected. So this is the better arrangement than the previous one, but of course it requires additional cost. It will incur additional cost. Dear learners, in this lecture, we started with a discussion on the basic layout of single-phase house wiring. We learned how to determine the number of subcircuits, switchboards, and distribution board. We then explored how to select the appropriate cable and breaker sizes based on the loads and other factors. Finally, we have discussed two wiring schemes for single phase installations with multiple distribution boards. In the next lecture, we will discuss the different types of wiring. I hope the information shared in this video has helped you enhance your understanding of house wiring. Thank you.